Help AP Chemistry Review live stream. Today we're going to be going over a few free response questions that you'll probably see on the AP Chemistry exam on May 2nd. So before we get into the questions, we're going to talk about the exam just for a bit. So we're going to look at what you want to, or what you will expect on the exam. So this is the free response section. So there's going to be 7 free response questions, and 4 of them will be long answers, which will be part maybe A through E, and then the other 3 will be short response. So you'll still get a few more parts, a little less parts, maybe like A through C. Although there are fewer parts, it will be probably take you about the same time to answer the same questions. So, and the exam length is also about an hour and 45 minutes long, so plenty of time to go over, check your work, and plenty of time to answer those 7 questions. So let's get straight into the first question. So our questions come from last year's 2021 free response section of the AP Chemistry exam. So we start with question 1. So methanoic acid, HCOOH, ionizes according to the equation above. Write the expression for the equilibrium constant, Ka, for the reaction. So when we look at the equation that they're given, and we think of a Ka reaction or a K equilibrium constant expression, we're going to look at the equation like this. Lowercase a plus B, and then our equilibrium arrows, because it is an equilibrium expression, yields C plus D and D. Now when we look at these letters, our lowercase letters are going to represent the coefficients in front of our compounds. As we see that there's no coefficient in front of these compounds because they're all the number 1. So if there's 1, then you don't need to really put it in because you can already represent it as the single compound. The capital letter in our expression represents the actual compound itself. So A in this case would be our methanoic acid, capital B our water, and so on. Now when writing the K expression, we go down, we represent it as bracket C raised to the lowercase c power D to the D power, and that is all over our A to the A power and B to the B power. So however many coefficients we have, we raise its respective letter to that value. So when we look at our expression, we look at the products first because of C and D, and we can write our first expression. We have our hydronium, and since there is a 1 in front of it, it's raised to the first power, but you don't need to write the 1 in there because it's already represented as a singular compound. And then we write our base, and that goes over our reactants. Equals our Ka. Notice that in my expression, I did not include the water. That's because when we write a Ka equilibrium constant expression, solids and gases, or solids and liquids, will not be involved. So whenever you see a liquid or a solid, you will not be included in the final answer. So with that being said, this is our final answer for our equilibrium expression. All right, moving on to part B. Calculate the pH of a 0.25 molar solution of methanoic acid. The way we want to approach this problem is by looking at what compound we are working with. So when we want to find the pH of an acid, we first want to think, is it a strong acid or a weak base? Or a strong acid or a weak acid? So looking at methanoic acid, we can see that it is a weak acid. And there are, in our equation sheet, you can see, and you were given the strong acids and weak acids. So when we want to find the pH for a weak acid, we write out our formula. And now, so we have our formula here, and when we want to solve for pH, we want to make what we call an ICE table, which stands for initial, change, and equilibrium. And those words represent the concentrations that our compounds will be at in the expression. So initial concentration of all of our compounds, the change in concentration, and our equilibrium concentrations. We want to use the equilibrium concentrations in our expression whenever we want to solve for our Ka value. So, first of all, like we said before, when we have our expression, liquids will not be involved in the Ka expression. So we can just put a nice X through there and not worry about the water in this ICE table. So we look at our initial concentrations that we're given. So it says 0.25 molar methanoic acid. So we can put our initial concentration as 0.25 molar. And now we look over to our product side of the reaction. Since it's the products, nothing has been created yet. So our initial concentration for our hydronium would be 0, and our methanoic acid ion to be 0 as well. Now we look at the change. Whenever the reactants are going to the products, it's going to be losing a reactant to create product. So we have a change in X, and because it's losing its molarity, and now the products are gaining concentration, so it will be an addition. The change can be dependent on the coefficients like we had before. The reason I have minus X and plus X is because, like we said before, the coefficient is our 1 in front of all of our ions and compounds. If the coefficient was 2 in front of our methanoic acid, it would be minus 2X, and so on. So now we can look at our equilibrium concentrations. And this is simply just combining the two, initial and change. So our final equilibrium would be 0.25 minus X, and then X for down here. So now, what do we do with our equilibrium concentrations? Well, like I said earlier, we plug it into our expression that we found earlier. So we had our concentration of methanoic acid. Our concentration of our hydronium times our concentration of our ion all over the concentration of our methanoic acid. And that equals Ka. So now we just need to plug in our values for our equilibrium concentrations. So I will just erase this, and now we write out our expression. So in the top, our concentration of hydronium was X times the concentration of our other, which is X as well, all over 0.25 minus X equals Ka. And right here in the problem, we see we are given the Ka value. So we can just put 1.8 times 10 to the minus 4. Now, what we need to do is solve for X now, because when we want to find pH, we do the negative log of our hydronium ion. And that is what our pH will equal. So if X is our concentration of our hydronium ion, we need to solve for X. So to make this a little more simple, if we examine the Ka value, we can see that it's times 10 to the negative 4, which is a very, very small value. So when we're subtracting X from 0.25 to get 1.8 times 10 to the negative 4, that's going to be a very, very small number of X to where it's going to be very negligible to be subtracted from 0.25. So we can get rid of that and make it a lot more simple. So now we can just solve for X by simply pulling out our calculators, and we're going to do 1.8 times 10 to the negative 4 times 0.25. So that will be equal to X squared, because we have these two X's up here that are multiplied to each other. So we take the square root of that, and we get our value of X. So X, So X will be equal to 0.0067. We want to make sure we only use two significant figures in this, because our significant figures that are given are 2 right here with 0.25 and with our K value of 1.8. So now X also equals, like we said before, our concentration of our hydronium ion. So we can come over here and do the negative log of 0.0067, and that will give us a value of 2.17. And this will be your pH for your methanoic acid at a molarity of 0.25. Alright, part C. In the box below, complete the Lewis electron dot diagram for methanoic acid. Show all bonding and non-bonding valence electrons. Okay, when we want to approach the Lewis electron dot diagram, we want to first count the number of valence electrons that we are given for every single element that's in the compound. When you want to look for valence electrons, you look for what group the element is on the periodic table. So you'll be given a periodic table on the exam on your equation sheet, so you don't need to worry and you don't need to memorize these numbers. So when we look at methanoic acid, we're given that there are two hydrogens, and since hydrogen is in group 1, there's one valence electron for every hydrogen ion that we have. So that means we have 2 electrons there, and now we have 1 carbon in our compound. And then we can see that the 1 carbon is in group 4, so that's going to be 4 valence electrons. And then there's 2 oxygens left, so we have 2 oxygens, and that's going to be in group 6 for the oxygen, and since we have 2, there's going to be 12 electrons. So we just add up and see how many total electrons we have. That will be 18. Alright, so now we know how many electrons we need to put into our electron dot diagram. So we want to first draw the bonding electrons to our each respective element. So we can do that by just drawing a single line, and that represents 2 electrons that will be connected to it. So we've used 2, 4, 6, 8 electrons in our initial bonding. So now we're left with 10 electrons that we need to put in our table. So where do they go? Well, we need to satisfy the octet rule for all of our elements, and that means that there needs to be 4 pairs of electrons on every single element. So on our central atom we have carbon, which already has 3, so we're going to put 1 more, a double bond on our oxygen, and then we're going to put double bond, or 2 here, and then 2 more here. So we count how many we just used. So we used 2 here, 4, 6, 8, and 10. So 10 more electrons we used. So now we have run out of electrons to make our Lewis dot diagram. So how do we know that this is the true electron dot diagram for our methanoic acid? Well, we need to look at the formal charges of each ion or each element that is inside the electron dot diagram. The formal charge is essentially the same number of the valence electrons that we have in our elements. So hydrogen is 1, oxygen is 6, and carbon is 4. So the way we count the formal charge of each element is we look at how many bonding pairs there are and how many electron non-bonding pairs there are. Now keep in mind that I've used lines on the outside for my non-bonding pairs, but if we have an element that looks like that, we can also represent the electrons as that, and you can see that each dot represents a singular electron. An electron will always be bonded with another one, so you'll always see 2 electrons on an element. So when we look at our formal charge of our elements, we count how many pairs that are bonded to it. So let's start with hydrogen. So we have our formal charge of 1, and we count how many pairs of bond of electrons are on it. So there's 1 right there, so that works. And we look at carbon. We know that carbon's formal charge is 4, and now we count the bonding electrons to it as well. So there's 1, 2, 3, 4 bonding electrons, and that equals 4. So that's good there. Now we look at our oxygens. Now we need to now this gets a little tougher because now we need to count the non-bonding pairs on the electron or on the element. So we count how many bonding pairs we have. So we have 1 here and then 2 on the other side. So now when we count our non-bonding pairs, we want to count them as if they were singular electrons over here. So 1, 2 instead of just a singular 1. So we have 1 bond here, 2, then we have 3, 4 electrons on that, and 4 and 5, or 4, sorry, 1, 2, 3, 4, 5, and 6. So 6 oxygens right there. And now we look at our hydrogen, and like we said before, there's only one pair in there, so that works with its formal charge. And this oxygen, we will count the electrons, so we have 1, 2, 3, 4, and then 5 and 6. So those formal charges check out. So we can tell that this is our final answer in the true electron-Lewis dot diagram. All right, now moving on to part D. In aqueous solution, the compound H2NNH2 reacts according to the equation above. A 50 milliliter sample of 0.25 molar H2NNH2 is combined with a 50 milliliter sample of 0.25 molar methanoic acid. Part I, write the balanced net ionic equation for the reaction that occurs when H2NNH2 is combined with methanoic acid. So, we're looking at our two compounds that we're given. So we're given H2NNH2 right there, and HCOOH. Now, we're going to combine these two so we can write our initial reactants because we know we are given these. So, when looking at this equation, we can tell that this will be an acid-base reaction because we're given an acid, as in the name methanoic acid. We can also identify this as an acid because methanoic acid contains that hydrogen bond right there. That single hydrogen atom is what makes most things acid. And we can identify this as a base because it contains nitrogen. Whenever you see those nitrogen-containing compounds mixed with another hydrogen-containing compound, you can see that it'll be an acid-base reaction. So how do we write the net ionic equation? Well, we have our reactants, and then we know that it's going to be an equilibrium because we're given it as an equilibrium expression. And so we're going to also write, so when we think about our acids and bases, we want to think of it as our Bronsted and Lowry acids and bases. So the definition of a Bronsted-Lowry acid is that it's going to be an H plus donor. So it's going to be giving away that H plus ion that made it the acid. And a Bronsted-Lowry definition of our base is going to be an H plus acceptor. All right, so now that we know that this knowledge, we can now write our products of what we're going to receive when we combine the two compounds. So since our methanoic acid will be an H plus donor, it's going to give that hydrogen to our base. So now our base is going to be H3 in H2. And we're also going to have a plus charge on top of it because it was once a neutral compound, and when it gained that positive hydrogen, it became a positively charged ion. Now, we can look at our methanoic acid that just lost that positively charged hydrogen, and so it's going to be a negative COOH, the negative charge at the end. And when we look at it, we can confirm this is our net ionic equation if we can see the overall charges on both sides. So we have two neutral compounds on this side, which will make a overall charge of 0. And we look at this side, we have a positively charged compound and a negative charged compound. Well, it can be the same as having a positive 1 minus 1, and that also makes a neutral on the side. So we need to make sure when we write our net ionic equation that we have the same overall charge on both sides, otherwise that will not be your correct answer. But since this checks out and we have already confirmed it, this is our final net ionic equation for part I. And one more quick note for the exam, you can also add your states of matter on here. As we know that we're given these are all aqueous because they're in the net ionic equation. In a net ionic equation, you'll mainly find these, but on the exam, you'll still receive full points if you don't include your phases. All right, part I. Is the resulting solution acidic, basic, or neutral? Justify your answer. Now, we did notice that I did say that our net ionic equation had a positive and minus that made neutral, but we can't just go off of our charges in the equation. For determining if a solution is acidic or basic or neutral, we want to look at our Kb and Ka values of the compounds that were mixed together. So in this equation, we're given the Kb value of our base. So we have a Kb of 1.3 times 10 to the negative 6. And now we need to look at the Ka value of what it was mixed, of the acid that it was mixed with. Well, we have methanoic acid, and we can tell that this is the same problem and we're still on problem 1, and we know that back on part A, we were given the Ka value of 1.8 times 10 to the negative 4. So we can simply go back and enter 1.8 times 10 to the negative 4. Now we need to compare the two and see if the solution is acidic, basic, or neutral. Well, when looking at this, we can see that the Ka value of our acid that we combined with our base is larger than our Kb value. With that being said, we can now justify that our solution will finally be acidic. All right, moving on. When a catalyst is added to a solution of methanoic acid, the reaction represented by the following equation occurs. So we have our methanoic acid, and it's going to be split up into two compounds, hydrogen and carbonate, or carbon dioxide, carbon dioxide. Is the reaction a redox reaction? Justify your answer. So when we look at a redox reaction, redox is short for reduction, oxidation. The term reduction is used whenever a molecule gains an electron from another molecule or atom, making it a more negative charge, or losing more charge because an electron has a negative charge. And oxidation is given from the term whenever it loses that electron, meaning it will become more positive. So it can be a little confusing because the oxidation agent is the one that will be gaining the electron, and the reducing agent is the one that will be giving the electron, because the reducing agent is reducing the other ion. So when we look at our question, we want to look at the oxidation states of our compounds. So the first one that can be particularly easy is we see hydrogen is in its ground state on this side. So we can see whenever any molecule or ion is in its ground state in a redox reaction, it has the formal charge, or the oxidation charge, of 0. So if we want to look at this side now, we can see that we have hydrogen, carbon, oxygen, oxygen, and hydrogen. So we know that the oxidation number for hydrogen is +1. And so we have a +1 here and a +1 there. Now we also know that the oxidation number for carbon is 2+. And oxygen, we know, is 2-. We can look at these values by looking at the periodic table, and we know based on their group number that where their charge will be. So group 1 will have a +1, group 2 +2, and then over on the other side we have our anions, where oxygen is in group 6, so it will be a -2 charge, and then carbon is in group 4, which means it will have a +2 charge. So when we look over here on this side, we want to see if there's an actual change in our oxidation numbers for our carbon and our oxygen. So when looking at our oxygen, we can see that there's 2, which means that our oxidation state for this one is now, it's still 2-, but since there are 2 of them, it's really 4-, which means this carbon is going to be a 4+ charge. So when we actually look at this, we can see that our oxygen went from +1 to 0, which means it accepted an electron, and our carbon went from 2+ to 4+, meaning it lost electrons, because when you lose something negative, it's going to become more positive. So we can actually see how it gained 2 positive charges, and the 2 hydrogens over here lost a charge, which meant that it went to 0, so it lost 2 and then became +2, and the hydrogen gained 2, so it became 0. So we can confirm that yes, this is a redox reaction. in your justification, you can talk about the charges of your carbon and your hydrogen, and talk about how it changed from 2 to 4, and your hydrogen changed from 1 to 0. All right, moving on to, we have part F, which will be the reaction occurs in a rigid 4.3 liter vessel at 25 degrees Celsius, and the total pressure is monitored, as shown in the graph above. The vessel originally did not contain any gas. Calculate the number of moles of CO2 gas produced in the reaction. And we need to assume that the amount of CO2 gas dissolved in the solution is negligible. So, the really important thing here is that we can see that the vessel originally did not contain any gas. So we know that the total pressure, when it increases, is going to be twice the amount of the gas that we have in our vessel. So we need to figure out how many atmospheres of carbon dioxide we actually have. So we know that 24 atmospheres total are in at the end of the time of the reaction. So we want to find how many atmospheres we have of carbon dioxide. So we want to get rid of the atmospheres total in the reaction and just end up with the atmospheres of carbon dioxide. So if we want to get rid of atmospheres total, we put that in the bottom of our multiplication or our division. So we have atmospheres total in the bottom, and we have atmospheres of carbon dioxide in the top. So we have, since we determined that it increases at half the rate of the total, we know that for every 2 atmosphere of product total, we have 1 atmosphere of carbon dioxide. So we can simply divide, we can cancel these and be left with atmospheres of carbon dioxide, and then we do our multiplication and division. So 24 times 1/2, we'll have 12 atmospheres of carbon dioxide. Now we can get onto the problem. So we want to look for the number of moles of carbon dioxide that are in the reaction. Well, we can use this by looking at our equation sheet, and we know that we are given the volume, the temperature, and we have the pressure now, and we know we need to find moles. So if we look at our equation sheet, there is one equation, the ideal gas law, that contains all of these values that we need to solve for. And that is represented in PV equals nRT. So we have P representing pressure, V is volume, equals N, which is number of moles, so that's what we'll be solving for, RT. So R in this case is the ideal gas constant that we'll be using, and that will also be given on your equation sheet. And T we know is temperature. It is important to note that in this problem, when we have temperature and is given in Celsius, we need to convert to Kelvin. So the conversion for Celsius to Kelvin is 25 degrees Celsius plus 273 equals our temperature in Kelvin. So we always just add 273 to convert to Kelvin. So now we want to solve for N, or the number of moles. So when we do that, we divide by RT. So our true equation will be PV over RT equals N. So now we can write our values in. So our pressure, we have 12 times our volume, 4.3, divided by our ideal gas constant, which is, in an equation sheet it's given, it's 0.08206 times the temperature, which we just identified as 298 degrees, or not degrees, just 298 Kelvin. So we calculate that out, we can see what we get. So 12 times 4.3 divided by our constant times our temperature, and we are left with 2.1 mole of CO2. And this will be the answer to our problem. All right, we have finally reached question 2. So, answer the following questions about the element silicon and some of its compounds. So, the mass spectrum of a pure sample of Si is shown below. How many protons and how many neutrons are in the nucleus of an atom of the most abundant isotope of Si? So, our key word here is isotope. So, an isotope is going to be a form of an element that can have a varying number of neutrons in it. It's written in this form. I just used the Z as the mass number. So in this, we have Z equals the mass number of our element, and P is the number of protons. It can also be represented as the atomic number, and then A, we have our actual element. So when we look over here, we can see that we have mass, and we want to look at the most abundant isotope, which is 28. So as we can see that the mass is 28 of this, and we have the Z as our mass, we have 28 Si, and our mass, or our atomic number, or the number of protons we have in our silicon, which if we look at our periodic table, the atomic number is the same number of protons it has, which is 14. So we have this isotope, but this is not our final answer. Remember, it is asking for the number of neutrons in the nucleus that we have and how many protons. So this is where our mass number comes in. Since we figured out that 28 was the most abundant, we can do what the equation is. The mass number equals the number of protons plus neutrons. So if we know that our mass number is 28, and we know that we have 14 protons because of the atomic number, we can easily solve for how many neutrons we have. So we just subtract 14, and we have 14 neutrons and 14 protons in this isotope. And that will be your final answer. All right, moving on to number 2. The mass spectrum of a pure sample of Si is shown below. Write the ground state electron configuration of Si. All right, so based on this, we're going to need to look at the periodic table and see what the electron configuration will be. So when you pull out your periodic table, you'll look at the different orbitals that are in the periodic table itself. I'm going to go to the next slide real quick just to represent that. So we can see we're looking for the electron configuration of silicon right here. So how do we write that? Well, we know that our orbitals are represented in S and P for this portion of our periodic table. So when we look at our S orbitals, we start with the first one. So we have hydrogen and helium in our first orbital. So that will be 1s. And we know that our s orbitals can hold up to 2 electrons. So we represent that as a square. Now we move on to the second section. And we have right here, we have 2s, because now we move down to our next in number. So we have 2s squared, because 2 electrons can be held in our s orbital. Now we go all the way over here to our other section, which will now be represented as our p. The way we recognize that the electrons can be held in here is by representing each element as essentially 1 electron. So we have, when you looked at our previous one, we had 2s squared. We have 1 here and 1 here. So now we move on to this section, and we have our p orbital. So this will be 2p to the 6, because we have 6 elements in that group. Then we move down, and we have 3s, 2 elements, squared. Now we finally reach the area where we want our aluminum and our silicon. So we have our silicon, and we know that it's in the 3p orbital, but we only put squared because it has only gone to Si2, and there's only 2 electrons that the Si can go up to. So when we go back to this problem, we can represent it as 1s2, 2s2, 2p6, 3s squared, 3p squared. So this can be our final answer. I will note that there's also another acceptable answer, which I've already written up here, and that is, you can see that we have the ending 3s squared, 3p squared, but we have this neon right here. And this is a shortcut that we tend to use in chemistry for electron configuration whenever an element is really far down and we don't want to write a really long chain of the electron configuration. So we find the nearest noble gas and we put it in brackets, and then we continue. So if we go back to the next slide where it is, we can see that the nearest noble gas before going over is neon, like we said. So we can always write it. We can still write it in Ne, and then we go to the 3s squared into our next one, and then our 3p squared. And that will be our final answer on this slide. So now we move on to the next question, which we already were on this page, and it is, write the ground state electron configuration of Si. So, actually, sorry, we move on to the next question on this slide. Two compounds contain Si are SiO2 and SiH4. At 161 Kelvin, SiH4 boils, but SiO2 remains a solid. Using the principles of interparticle forces, explain the difference in boiling points. Now, when we use the phrase interparticle forces, those are the forces that are contained inside our different compounds that actually hold those elements together. And they all range on different strengths and different criteria of what is actually in that compound itself. So we know that we have hydrogen bonding interparticle forces, which will be our strongest force. And then we have dipole-dipole, which is our next strongest force. And we also have London dispersion forces, which will be our weakest. So, when we look at our part B, we have SiH4. Now, how do we know how many forces there are in this? So, we can figure out if it has London dispersion forces. We know that every single compound will have London dispersion forces when we draw out its Lewis dot diagram. We can see that in this molecule, it doesn't contain a dipole because this is a non-polar Lewis dot diagram because it is even on all sides and it has a tetrahedral shape. We can see that it does not contain any dipole-dipole because it's non-polar, because it's even, and we can see that it contains no hydrogen bonding because for hydrogen bonding to occur, we need our hydrogen ion to be compounded with O, F, or N. So as we see, there's no O, F, or N in the silicon, so we know that there's no hydrogen bonding. So the only dispersion, or the only interparticle forces that are in this compound are London dispersion. Now we look at SiO2. When we look at this, we can see that there's really no dispersion forces because this is a covalently bonded compound, so it has those covalent bonds, which are weaker than London dispersion forces. So when we look, we have this. And so we have London dispersion stronger than covalent bonds. So how does this affect the interparticle forces at the temperature? So when they're at the same temperature, since our London dispersion forces are strong, actually, I apologize. These will be stronger because when we're at the stronger side, we have a solid, and then at the weaker side, we have a boiling liquid. And that's because at the certain temperature, it'll be much easier to get rid of the London dispersion forces than it will be to get rid of those covalent bonds. So the way you explain is you can draw out your Lewis dot diagram and figure out what actual intermolecular forces are contained inside of each compound, and then you can determine why they are at each different state of liquid and solid. So, at high temperatures, Si4 decomposes to form solid silicon gas. So, we can look at this question right here. So when we look at a decomposition expression, we can look at it and represent it as AB yields A plus B. So this is what a decomposition reaction looks like when we look at it in chemistry terms. So we have silicon, and then it converts into A and B. So if we look at silicon as our A and hydrogen as our B, it can convert into Si plus hydrogen. Now when we look at this expression, or equation, we can see that it's still not balanced because there's 4 hydrogens in this compound. So we put the 4 there in front, and we have a balanced equation, which will be your final answer. Alright, explain why the absolute molar entropy of SiS is less than that of H2G. Remember when we look at these parentheses, we can see that that S represents solid, and this G represents gas for H2. So, why is the molar entropy of silicon less than that of H2? Well, we can go here, and we can look at our absolute entropies of the substances given below, and we can see that H2 has 131, Si has 18, and SiH4 has 205. So we can definitely determine that Si has a lower entropy of hydrogen gas. So when we look at SiO4, or SiH4, we can see that it's made up of molecules, and that we can determine this with their intermolecular forces. And like we said in the last problem, their intermolecular forces, or interparticle forces, are London dispersion forces, which are relatively weak. And we know now that it's split up, we have Si in solid form and H2 in gas form. So we know that when we have a solid, we know that its particles are very tightly compact in like a row, and they're very rigid and very close together to where they do not move. And we know for a liquid, or they're a little more dispersed out, still closer, but they're freely moving. And then we know for a gas, they're very spaced out and moving a lot. So when we look at the solid and gas, we know that since these atoms are in a fixed position and are less dispersed, and the atoms for the gas are more freely moving and a lot more dispersed, we know that it's going to take a lot more. It's going to have a much higher molar entropy, which is determined with S, than the gas. So we know that the solid has a higher molar entropy than the gas. Calculate the value in joules per mole Kelvin of delta S for the reaction. So we're given the table of entropies, and we can determine the absolute molar entropy based on this using an equation that will be given on the exam. So we can determine this by doing molar entropy equals the moles of our product, which we determined before, note that in this one we have hydrogen, which is diatomic, so it's going to be in its ground state. It will always have 2, and so to make it balanced, there will be 2 as the coefficient to have 4 and 4. So we'll have the moles of our product, which is hydrogen, plus the moles of our other product, which is silicon, and we're going to add that to the moles of our reactant, And whenever we represent our molecule, it's going to be the delta S number given in the table of that specific compound. So we can solve this by doing delta S equals moles of hydrogen. We know that the coefficient in our expression represents the moles of our actual compound. So we have 2 times our entropy of it, which is 131, plus our moles of silicon, which is 1, times the molar entropy of it, which is 18. And there's a quick correction to be made. This should be a minus sign because we're subtracting from our products and our reactants. So that is our that's our product side, and we'll subtract from our reactant side, which will have 1 mole, because there's only 1 in front of it, of 205. So when we get our calculators out, we'll do the simple calculation. It'll end up overall being 280 right here. Subtract 205, which will get us an overall entropy of 75 joules per mole K. All right, moving on to part F. The reaction is thermodynamically favorable at all. Ooh, it looks like my laptop just died. Sorry, technical difficulties. We have our laptop just died. Alright, so if we want to represent this equation, let me just grab a pencil and paper. 1 second. Alright, so for the correct explanation of this problem, we know that a high temperature is required for the reactant particles to have sufficient thermal energy to overcome the activation energy for the reaction. So whenever we have an actual reaction in thermodynamics, there's always going to be a certain temperature that will be required to actually make the reaction. So if there's a reaction that needs a specific energy to actually occur, and we don't have the heat to get there, the reaction will not occur. So when we know that the temperature is favorable at only high temperatures, we know that it will need a very, very high temperature for the actual activation energy to be overcome so the reaction can proceed. All right, we're back. Yeah, so like we said before, we have it's thermodynamically favored at all temperatures, and we explain why the reaction occurs only at high temperatures, because it needs, when we look at the actual energy for a reaction that is in thermochemistry, it will look somewhat like this for the energy, and it'll come back down. So this peak right here that goes really high up is what the actual activation energy is. So the energy that we need have to be really high temperatures for it to actually overcome this to proceed to the reaction, which will go on to make our products. All right, moving on. A partial photoelectron spectrum of pure silicon is shown below. On the spectrum, draw the missing peak that corresponds to the electrons in the 3p sublevel. So, going back to silicon, we already wrote our electron configuration for it, which we can represent as 1s squared 2s squared, 2p6, 3s squared, and 3p2. So when we look at this relative, we can see that there's relative number of electrons represented in these graph lines right here. So we can go over here and just put 1, 2, 3, 4, 5, and 6. And now we can just go through our electron configuration and we can look at the electrons that it has. So we can see at this, it has the 1s. So this is our 1s squared. We move on. We have our 2s squared. Then we move on. We have our 2p6 because we have 1, 2, 3, 4, 5, 6 electrons, and then 2 here, and then 2 here. That's where we're getting our squared values and 6 value from. So then we can just cross off what we have already. And now we have 3s squared next, and we can see that that matches with the 2 electrons here. 1, 2. And so now we're left with 3p6. So now we know we can just simply draw that by going up, or 3p squared. So we can go up to our 2 electrons, and that's represented as our 3p squared, and the missing peak for our electron configuration. All right. Using principles of atomic structure, explain why the first ionization energy of GE is lower than that of SI. So, when we look at GE on the periodic table, we know that it has a higher shell, or it's in the n equals 4 orbital, and we know that SI is in the n equals 3 orbital. We can look at that by just looking at the groups of the group. So if we go down the periodic table, we can look at our periods, actually, or our rows. So since we have GE in n equals 4 orbital, it's going to be much larger. So if we have our nucleus in the middle of GE, we know that its orbital it's going to have a higher orbital, which is going to be further away from the nucleus, that will have its electrons on the outside. Now if we look at our n equals 3 on our silicon, we'll have a nucleus, and then it'll be a little bit smaller because it's in n equals 3. So it's going to be a little bit closer to the nucleus. So when we look at ionization energy, that just stands for how easy it is to remove an electron. So we know that the first ionization energy of GE will be much lower than that of SI because it won't take as much to remove an electron that is further from the nucleus, because this nucleus is going to be pulling those electrons into it because it has the protons and neutrons into it. So something that's much closer is going to have a much stronger pull, so it's going to be a lot harder and require a lot more ionization energy to remove that electron. So we move on to our final question, which is a single photon with a wavelength of 4 times 10 to the negative 7th is absorbed by the SI sample. Calculate the energy of the photon in joules. So, using our equation sheet that we were given on the exam, we can know that E is equal to HV, and we know that we have our other formula, which is V equals C over lambda. So we can combine these two because we know we're given wavelength, and we look at H, we know that this is a Planck's constant. So we can look at this and we can write our final equation to be E equals H C over lambda. Like we said, we have our wavelength, which is given in meters. So we have 4.0 times 10 to the negative 7th, and we have H as Planck's constant, which will also be given on the exam. It will be written as H equals 6.626 times 10 to the negative 34 joules times seconds. And we know that C in our equation sheet is the speed of light, which will be given as 3.00 times 10 to the 8 meters per second. So, with all of our information, we also know that lambda is represented as the wavelength, 4.00 times 10 to the negative 7th. So, we just plug in all those values, 6.626 times 10 to the negative 34 joules times second times 3 times times 10 to the 8 meters per second, all over our wavelength 4.00 times 10 to the negative 7 meters. And that equals our energy. So when we do our calculation, we will get an answer of E equals 4.97 times 10 to the negative 19. Now, what are our units? Well, the question did ask for it to be in joules. And we know that J is representative of joules. So if we go through our equation, we know we have meters on the bottom and on the top, so those meters will cancel. We know that the seconds on this will also cancel. So we are left with joules. So this will be your final answer. Okay, so that was our last question, unfortunately, and all the time we have for today. But don't worry, on Sunday we will have another live stream going over some more free response questions. They'll have a lot other different topics on it because this is just a very small amount of other things that will be on the exam. So don't worry, you can tune in at the same time on Sunday, and we'll go over a lot more exams questions and just to get you more prepped for that impending exam. I hope that this helped, and have a great day.